week 6 of hcin 600 research methods. And one of the things you'll notice if you look at the content section in my courses for week 6 is we are now starting to talk about statistical analyses, and that's what this video is about. So if you look at the content section a little bit further, you'll notice there are a bunch of files here. And if you just open these files, they're not going to make sense. In fact, you won't even be able to open them directly in my courses. My courses doesn't understand the file name extensions of these files. So except for the PDF course notes, which are my notes from a statistics course that I took, Practical Statistics for HCI. And this course uses free and open source software called R. That's the letter R, capital R. And I would like you to download R, and I would also like you to download an IDE for R called RStudio. So let's do that right now. So I'm just going to Google the letter R, which auto-completes to RIT, which is good, but not what we need right now. And what we want is the very first hit that comes up, the R project for statistical computing. So this is a really outstanding piece of software for running statistics. Because it's free and open source, it's there's no administrative overhead in running it. You just download it and use it. Unlike a lot of statistics programs where you have to be concerned about the license and purchase orders and license renewals, and accountants get involved and system administrators get involved, and it's complicated and annoying. Free and open source software isn't like that. The people who are involved are just the contributors to the software, of which there are many for R, and in fact R is the choice of professional statisticians worldwide. I don't think it's any exaggeration to say that this is the main piece of software that's used by professional statisticians. So, and it is kind of a pain to learn, so I want to take you through some of it. So I'm going to click on there, and then I'm going to say getting started. I want to download R. Of course, I already have R, but let's just, for the sake of argument, suppose I don't. So I'm going to go to a mirror of CRAN. CRAN stands for the Comprehensive R Archive Network, and it contains thousands, if not millions, of packages for R. And I always choose this one, usually choose this one. And I'm on Mac, so I choose Mac OS X, and then I choose latest release. And here's the latest release. And I already have this, so I'm just going to cancel, but there's an install procedure that I'd like you to go through and install this software package. Then after you've installed that, I'd like you to install RStudio. So I just Google RStudio and I get RStudio here. Actually, it probably would have been faster from Google to go to download RStudio. And I'm going to choose the free version. Of course, there's a $1,000 a year version and a $5,000 a year version that keep the lights running at RStudio, but the free version is sufficient for almost all purposes. I should say the others give you some services that are really valuable, but and then I'm going to go Mac OS version 10 or above and choose this one. And again, I have this already, so I'm not going to download it, but I'd like you to download it and install it and open it. And when you install it and open it, you'll get this, except you won't have this file. So you have to go back to my courses and download these files. So let's go back to my courses. And I want you to download stats1.rmd, bookflights.csv, and IDE2.csv. So download all three of those files. And then come back here and say open file. Make a note of where you've downloaded them. And oh, I'm not in the downloads folder. And go to downloads folder, and I have stats1.rmd here. Now I have it open, so I'm not going to open it. And I want to make this my current working directory because I've also downloaded ide.csv, or rather ide2.csv and bookflights.csv, and they're all in the download directory. So I want to set working directory to source file location, and so you can see that that ran this command, set wd to downloads. That's where my downloads are. So that's where this file is, and the other two files that we're going to use. Now this file, stats1.rmd, is called an R Markdown file. R Markdown is a literate programming style, and it means that the source code is bound up with the documentation all in one file. And so I can run this file and get all the documentation of it plus all the statistical results from it at the same time. And this allows me to do something called reproducible research. And reproducible research is a big deal now. So I'd like you to use this style, if you possibly can, for your assignments. And it would be great if you actually did your assignments, did some of your assignments in our Markdown files. You can include pictures and math equations and all kinds of stuff in an R Markdown file. It's a little bit steep learning curve, so I'm not going to expect you to do it, but I think some of the more enterprising students may find this interesting to do. So this file is a plain text file, but you can see that it's color-coded here. That's because RStudio understands it to be an R Markdown file and is assigning colors and other things. So for example, I can close the sections of it off. R Markdown interprets the pound sign as a section marker unless it's inside a chunk of R code, in which case it's interpreted as a comment. So these that are outside of chunks of R code are section markers. So you can see that the section markers for this document are Welch's t-test, ANOVA assumptions, Mann-Whitney U test, Likert scales, more on Likert scales in R. And this is called front matter. I can also collapse that. If we were to render this file, this would contain the metadata that would create a title and create an author line, and it also tells how it should be rendered. In this case, that it should be rendered as a PDF document, and that it should use this program XE-LaTeX to render it. But we're not going to render it. We're going to go through these chunks of code one line at a time so that I can explain them as we go along. Now what happens is when I do it that way, see, if I render the whole thing, it's just one shot deal. I think I can just press the run button and it'll render this whole thing as a PDF with all the statistics embedded in it. But I'm not going to do that. Instead, I'm going to run selected lines. So I'm going to use the command enter shorthand to run selected lines. And what that's going to do is put those selected lines down in this console area here and run them. So these are just lines of code in the R programming language. Now, as I mentioned, I got this from a course that I took on practical statistics for HCI, and in the My Courses folder is a rendered version. So this is a nicely rendered version of my course notes from that. So I did very elaborate course notes for that and customized them, made them look very nice so that I can use it as a cheat sheet when I want to do things, because nobody can remember all this R code. What you do is, you find the part that has what you want to do, and then you use the code that's in there. Here's an example of R code that's in there. Okay, so let me get back to this IDE. So I've got this stats1.rmd file open here. I happen to have some other files open just from other sessions. Just those are not important right now. This is a chunk of R code. So the R code is highlighted differently from the documentation part. And I say here in the documentation part, let's sneak up on the Mann-Whitney U test. So the first thing we're going to do is a Welch's t-test, and this is a parametric test. Some assumptions are involved, and so what we're ultimately going to do is a non-parametric test. But first, we're going to do this parametric test as if it were okay on this data set. So we have this chunk of our code that starts with 3 backticks and then the letter R in curly braces. And optionally, I can put other stuff in the curly braces after the letter R to control how this works. But I'm just doing the simplest possible thing now. Then inside of our code chunk, the pound sign or hash mark or sharp sign, whatever you want to call it, indicates a comment in the R language. So if I were to start a line that way here in the console, that line would be ignored by R. Nothing happens because of that. Now, the comment here at the beginning of this R code chunk says that the scenario is we're comparing task completion times and authoring tools. The authoring tools are IDEs, Eclipse and Visual Studio, and we're comparing how long it takes to complete a task using those 2 tools. So that would be a typical HCI experiment. And here are the statistics that are involved. And we're starting with the independent samples t-test. So the very first thing that we have to do is read in a data file with task completion times from 2 programming tools. And that's what's involved in this line right here. And I'm going to run this line by pressing Command Enter. And obviously on Windows you would do something different. And this only works because I have this file in the current working directory, this file ide2.csv. I've already downloaded it from my courses. It's already in my current working directory. And so I don't get any error message here. It just reads it in. And then I can say view IDE2. So I'm going to again press Command Enter. And I get a picture of the file or the object now. So what I've done here is create an object called IDE2 based on the contents of this file. It happens to be identical to that file in this case. So the contents include a line with headers. So we have the subject, the IDE that was used, and the amount of time in minutes that it took them to complete the task. And you can see that there are 40 entries here, and the subject number is commensurate with the line number. The boldface numbers here are just line numbers. They're not part of the file. And then either Eclipse or Visual Studio, and then the time in minutes. So with a tiny file like this, you don't really need to do a lot to investigate it. It's pretty easy to figure out, but we're going to do some stuff anyway. So the first thing we're going to do is convert the subject number. The subject number, you notice, was an integer from 1 to 40, and we're going to convert that to a factor so that it's no longer interpreted by R as a number, but instead is interpreted as just a subject ID. So this is a factor function that's operating on the object IDE2, and within that object, the $ tells us that the next thing is a column within that object. And this is an assignment statement. This is like the equal sign in C or Java. And so we're assigning it, to this same object the identity of factor instead of, and there you see there's a little tooltip saying what the factor function can take as parameters. Okay, so now I'm going to do the summary of this. And the summary of this is that we have all these subjects as factors. We have 2 factors of IDE, 2 levels of the IDE factor. Eclipse with 20 observations and Visual Studio with 20 observations. And then we have time as an integer, and we have some statistics about time. So we have that the mean is 385 and the median is 313. So those differ quite a lot. And that's because of this extreme outlier that's 952 minutes that some unfortunate soul, took to complete the task. We can also see it up here. So one feature of RStudio is that it has different windows for different things. And we can see IDE2 here. We see that it's subject is a factor with 40 levels. IDE is a factor with 2 levels. Time is an integer with the following values. Okay, now I want to view descriptive statistics by IDE. So these descriptive statistics here are just for the data set as a whole. I would like to see what the mean is for Eclipse versus the mean for Visual Studio, because our goal with this data set is to find out whether one of these IDEs works better than the other one, or is worked better in this task. So I'm going to go back here and install a package. Actually, I already have this installed, so I'm not going to run that. I'm going to load this package Plier. You will have to install it. And you'll get a lot of gobbledygook. Well, here, I'll install it anyway, and you can just see. And this is saying, oh, this is a package that I've already loaded. So interesting. So I guess I did this before I came on camera. So I'm going to restart the R session and then install the package, just so you can see what installing the package looks like. Now, you only install the package once, and then it's just there for you. And you have to load it using the library call. You have to load it from the library. That's where it's installed. So I've loaded it, and now I've done ddply. That's a function in the plier package, and the output is shown below my current R chunk. So here's the ending of my current R chunk, is these 3 backticks, and here is the output of that function. So you can see that it's showing us Eclipse and Visual Studio, and the means are wildly different, 468 versus 302. So I think that that's probably a significant difference without even doing any statistics. But I don't know that for a fact. For example, all of the times could be bunched around those 2 numbers. So if they're tightly bunched around there, then this may not be a significant, statistically significant difference. The max for Eclipse is really high, 952 minutes. That's a remarkable length of time for this task. It's an extreme outlier. And there are several extreme outliers in the Eclipse sample. We'll see that in a minute. So the next thing I want to do is another ddply, another call to ddply that's going to show us the mean and standard deviations. And this function is taking the IDE2 object as input and saying that we want to do this by, this part right here means that we want to compare IDEs, tilde IDE means to compare IDEs. Here we want to summarize, we want the mean of time and the standard deviation of time. So let's run that. And you see that the standard deviation for Eclipse is more than double what it is for Visual Studio. So let's take a look at a histogram of that. Here's a histogram of Visual Studio. And you can see that Visual Studio has some outliers too. And let's do a histogram of Eclipse. And Eclipse has more outliers and goes out to 1,000. The 952 is probably the only thing in this bin that is, well, you can see there's one observation here, there's one observation here, one observation here, 2 observations here, and so on. Okay, so now we'll do the independent samples t-test, and we don't necessarily know whether this is valid to do. And the reason that we don't know that it's valid to do is because it makes some assumptions. we've assumed, for example, that the variances are equal between the two, and they're not. The variances differ by quite a bit, or at least it appears that the variances differ by quite a bit. We don't know that that's a statistically significant difference, but we can check on that. So in terms of the means, the two-sample t-test tells us that the means differ. We know that because the p-value is extremely small. The p-value tells us the probability of seeing this result, or as a more extreme result if the null hypothesis is true. So we suspect that we've got some evidence to reject the null hypothesis here. These means do look very different on the face of it. So now, one problem is that we're relying on these assumptions. The ANOVA assumptions are independence, no observation effects, and other observation, normality, the residuals are normally distributed, and homoscedasticity, which is that the variances are homogeneous. I think that's misspelled. That should be homogeneous. Okay, so are these assumptions warranted in this case? So this next chunk of our code tests those assumptions. And this is all stuff that you hopefully learned about in a statistics class already, but you may have implemented it in a different language. So the first thing is a test for normality. And the null hypothesis is that they're normally distributed. So if we see a small p-value, which we do, that's evidence that they're not normally distributed for Visual Studio. And for Eclipse, we have the same situation. The small p-value suggests that they're not normally distributed. But what matters most is the residuals. Are the residuals normally distributed? So we fit a model using an ANOVA function. So this AOV is an ANOVA function, analysis of variance. And we call that the model. Model is an object. This is an object-oriented programming language, by the way. We call it M, and this is just an assignment operator. We can either use this as an assignment operator, or we can use the arrow, which I've used up above, as the assignment operator in R. R accepts either one of those. So now I lost my place. Okay, so now I want to do a Shapiro test of the residuals of the model. And here again, the p-value is quite small. In fact, it's even smaller. So that suggests that they're not normally distributed. And we can do a QQ plot. That's the most typical way of telling normality besides that test. And the QQ plot will appear at the end of this code chunk. And the QQ plot, all the dots should lie along this line if they're normally distributed. And of course, they way don't follow that. So we can also test whether log normality is warranted, whether an assumption of log normality is warranted, in which case we can just adjust these. And the Kolmogorov Smirnov test tells us, yeah, the null hypothesis is warranted in the case, at least in the case of the Visual Studio. Let's see if it's warranted. Of course, I've given away the ending here. Again, the assumption of normality is warranted for a log normal distribution, so we can just adjust. Now let's check homoscedasticity, and we're going to find heteroscedasticity is going to be the result. So I'm not going to install the package car, I'm just going to load it. And this warning message is telling us that we have two functions with the same name. And that's not going to matter today. That can matter in many cases, but for what we're doing today, it's not going to make any difference that we have two functions with the same name. Okay, so first we're going to do Levine's test, which uses the mean. And we get a very tiny p-value. So this is a test for homogeneity of variance. So the variances are not equal. We have the Levine's test telling us that there is heteroskedasticity present. And we get the same result from the Brown-Forsyth test, which uses the median. Not as dramatic as the Levine test, but still pretty significant. So we can actually run the t-test with unequal variances. We just say var.equal equals false. And that's going to give us the t-test without the assumption of the variances being equal, because we've verified that the variances are not equal. We've also verified that there's a violation of normality, though, and this doesn't solve that problem. So we can do a data transformation to try to solve that problem because we found that the logs were normal. So we're going to actually do a log transform here. So I'm going to create a new column, and I'm just going to verify that that column exists. So this is the log of the time. So this corresponds to time, but it's we're going to find that it's normally distributed. Okay, and then we can explore this just for intuition building. So we can do a histogram. And there's a histogram. It looks more normal. That's not a really good sign, though, and this does not look very normally distributed. That's the eclipse one. And we can do a box plot, and we see from the box plot that they differ quite a bit. So we're going to retest for normality, but we're going to test if log time is normally distributed. And we get that it is, and for Visual Studio. And then we're going to do it for Eclipse, and again we get a large p-value suggesting that it is. And we're going to run the Shapiro test again, so we're going to do the analysis of variance, fit the model, call the model M, test for the normality of the residuals of M. And here we get that they're normal. And we can do a QQ plot and see this graphically. And it's not perfect, but it's a lot better than what we had before. It's a lot closer to the dots all being on the line than what we had before. So this is pretty good. So we might accept this. Let's retest for homoskedasticity, and we're just sort of over the line for a 0.05 significance level. So I would say that we would say that the independent samples t-test is suitable if we use log time instead of time. And again, we get that they differ quite dramatically. Now, all these white blocks that show up here with a little X in the corner are not part of this file. I can just dismiss them. They're just the results. They show what would be added to the file if we rendered the file. I shouldn't say that. It wouldn't be added to the file. It would be added to the output file. So this would still be the same plain text input file. You can examine it in any text editor. Okay, so that's the end of that section. So now it's usually the case that we can't make those analysis of variance assumptions. So we use the Mann-Whitney U test. This is the most common test in HCI experiments because they're usually small, and we usually don't know if we've met the assumptions of analysis of variance. So we're going to get the Mann-Whitney U test out of the coin package. Oh, well, okay, I installed that. I didn't really need to because I already have it installed. And I load the package, and then it's called Wilcox_test, but it's basically the same thing. And this is similar to the t-test, except non-parametric, and we see that they differ. So, and we see that they differ both for time, and we see that they differ for log time. So we know that either one of these is an acceptable value to use. and we get the result that the Visual Studio is much preferred in terms of the time to task completion. Okay, now a really common thing that you're going, so now I want to switch gears completely. A really common thing that you're going to do is visualize Likert scale data. So I'm going to do this very common idiom. So this is an if-then statement, and it says that if the psych package is not loaded, can't be loaded, then install it. If it can be loaded, it will be loaded though. That's all that line says. And the same thing is going to happen. See, it's loaded psych and it's loaded Likert. So now I'm going to read in another file, the book flights file, which I also downloaded from my courses. And you'll see it appears over here. We've got, we've also got all this other stuff here. We added this when we created the models. Every time we created a model named M, it modified this entry right here. Okay, so I'm going to do tests. Let's see. Oh, I want to make international. So this, I really should view this. Do I view this anywhere? No. Let me insert a line here that says view BK and run that. And you can see that we have, I think 600 subjects. I can't remember how many subjects. I think 600 subjects. Yeah, 600 subjects and 4 columns. So there's the subject number, which website they used, whether the flight they tried to book was international or not, and their subjective impression of how easy it was to do it on a scale of, on a Likert scale, 1 to 7, I guess. And later we'll find out which one was easy and which one was hard, because we end up coding that in here. Okay, so whether it was an international flight or not is a 1 or a 0. We want that to be interpreted as a factor, so I change that to as factor. And I'm going to compare ease for international and non-international flights here. And I find when I do that, first of all, it's taking a long time to run that test. I don't know why. It's not that large of a data set. Could be because I've got a lot of other things running on my computer, and I've been somewhat haphazard about that. And we find that there's not a significant difference. So whether or not the flight was international or not didn't make a difference in terms of how easy people thought it was to book the flight. Now we're going to compare the 3 websites. So there are we're going to need 3. Is that right? Yeah, we need 3 comparisons. So we need to compare Orbitz to Expedia, Orbitz to Priceline, and Expedia to Priceline. So if we compare Orbitz to Priceline, we find that again we have a long wait. And this passes the 5% test. So I'd say there's a difference in how easy it was to book on those 2 websites. And again, this passes the 5% test. So I would say those 2 differ. And this last one does not even come close to passing the 5% test. So I would say Expedia and Priceline are about the same. Orbitz and Priceline are different. Orbitz and Expedia are different. Okay, now I'm going to create a new data frame here. So A is going to be the ease for Expedia, B is the ease for Orbitz, C is the ease for Priceline. Ease is going to be the name of the data frame, and the head of ease is just the first few lines of ease. So here are the first few lines of ease. So it's just a set of 3 columns each column containing the E's for that website. And the levels I'm going to say are range from 1 is very easy to 7 is very hard. And the items are Expedia Orbits and Priceline. And now I'm going to use the plot Likert. Now that can't be right. So I need to, let me do this. I'm pretty sure I need to do this to get that. Okay, so this is a plot of this Likert scale data, and you can see it doesn't look that different at all. Here are the 3 items, the 3 websites, and here's hard, here's very easy. And I can sort of see how, well, no, I can't. We got that Priceline and, seems to me we got the Priceline and Expedia were the same, not Orbits. I don't know, they don't look, none of them look that different to me, just graphically. So it's a good thing that we ran those tests because, well, by the way, I'll alter this. This statement will be, this function call will be in there. Okay, and then here's another example. So this is from the R companion. So this is a nonsense data set. So instead of entering a data set, so this is another Likert scale thing. And this is how much people liked these 3 characters in Winnie the Pooh. And I'm just, did I already install the, did I already? Yeah, those are already loaded. Okay, so now I'm going to highlight this whole thing and select it. So instead of adding something from a file, I've actually typed the data in here, and now the data appears here as input. Okay, and then I'm going to convert that into a table, so it'll now, so data will now appear here. If I run this, so see now I have data there, Pooh, Piglet, and Tigger. This is just how much people liked the characters or something like that. Then I'm going to change, so all the numbers are interpreted as numbers, and I want them to be interpreted as factors. So there it is for Pooh. There it is for Piglet. And there it is for Tigger. Okay, and then that gives me the head and the tail of the data set. I don't know why I did that. This gives me the str, gives me the structure of the data set, which I can also get over here. And here's a summary of the data set. Very simple data set. And I'm going to remove the original input for some unknown reason. Okay, and then we already have loaded this stuff. So I'm going to say result is Likert data. And now I want to plot the result. So this is going to give me a bar plot of the result. So, oh wow, and we see that, so if 5 is very much liked and 1 is very little liked, then people liked Pooh and Tigger the same and didn't like Piglet at all. Of course, this is nonsense data. Here's a heat map of the same data. So we see that these two are the most, or these three were the most frequently selected. We easily see that on a heat map. And then we can do also a density plot. And the density plot shows that Pooh and Tigger are similar, and Piglet is fairly different from the two of them. Okay, and then here's some additional readings to keep you busy on those long winter nights. Okay, now here's some stuff from a blog post that I read, and I've modified this code. So I actually don't need this, I think. So here I'm creating fake data just to demonstrate Likert scale stuff, and I'm saying, in this way that this fake data is I'm sampling from numbers from 1 to 2, and these are going to be floating point numbers ranging from 1 to 2, and I'm going to get 500 of them, and I'm doing it with replacement. So even if I've selected one, I can select it again, and this is the probability distribution. And the levels are, oh no, I'm sorry, this is not floating point numbers. These are just I think these are just agree and disagree. So I think these are just two, let's take a look here. I'm going to, I'm not sure. So these are 5 questions on which people agreed or disagreed, and I can't, yeah, this is just agreed or disagreed. So these are the fractions of people who agreed or disagreed. So that's one way to plot that. So it's going to be very common in your survey paper to have data that's amenable to this kind of plot. Yeah, so that was just agree or disagree. So here we have 1 to 4, so we have a scale of agree, strongly agree, and so on. And now here we have the graphical output of that. So this is 5 questions, and whether people agreed or disagreed, or strongly agreed or strongly disagreed. And here we have it from 1 to 6. So again, this is just all random data, just demonstrating the functions to you. And here it is on a scale of 6. So basically, you're just going to replace this with a making a data frame out of your raw data from your survey, and then typing in these, agree or disagree things, and what questions you have, and you can make a plot of the results. So it's a very compact way to show your results. And what's this? This is different. I've forgotten what this is. So let's look at this. Levels are okay, so here's an error in my code. I don't know what that is. I think I'll probably just delete that from this file, because I honestly don't remember what that. Well, I can show you the blog post that I got this from, and let's see if it tells us. Here it is. The URL is in there. Oh, that's these. Oh, okay, so that's these 2 things. use this sjp.stackFreak function. But I don't seem to have that function. So that should have been in the sjplot package. So that's a nice way, that's an interesting way to do this. But somehow I don't have that function. So at the beginning of his blog post, I think he says you have to load that package. Of course, this was done back in 2013, so the package may have changed. And so Stack Freak may have a different name now. People in this blog post, people commenting on this blog post actually asked for some changes in it. And that sometimes does happen. And it's a little bit tedious. Well, I may as well show you. So it's called sjp.stackFreak, I think. Oops. So this is shown as being in version 2.6. I have version 2.8.1. But it doesn't say that. Here's, well, from 1.8. But this doesn't say. So I wonder if that's changed now. Okay, plot stack freak. So I'm going to change this so it'll be changed in your, so it'll be plot stack freak instead. Okay. All right. So in the version that I give you, this will be corrected. All right. So that's all I have to say about that. There's another file in here, stats2.md. It's similar. It's a Markdown file instead of an R Markdown file, but it's similar, and you could, and then there are preferences expressed by males and females. Let's just take a quick look at those. That's pretty much, yeah, preferences expressed for 2 or 3 websites, and whether or not they were males or females, and the differences in those preferences. So it's just a way of making comparisons, using statistics to make comparisons. And that's pretty much everything that's in the stats2 file. So that's all that I have to say for now. I do want you to ask me detailed questions about problems that you have trying to run R, because I'd like you to use R. Of course, you're free to use whatever statistics package you want, but I prefer R, and I hope that you will come to prefer it too. It's a bit of a pain to learn, but it's very rewarding once you have learned it. So hit me with your questions, and I'll talk to you soon.